I wanted to jump into this next topic, though, not that we're really behind it all, but I think this is, hyper relevant for what several of you are going to be jumping into when you get started on your project. So texturing is technically part of MP4, but it doesn't look like it's going to be an achievable goal for MP4. So for others, that will still also fall into your project, and a couple of you are looking into lighting aspects as well. But to start with, I actually wanted you to try something today. Now, I know one of you has actually kind of played with this already for some of your demos, but I want you to think about this question because we haven't done a lot of modeling at all this semester. We've done kind of the bare minimum of how do we just create a triangle that looks like a triangle. And so what I'm asking you to do today is to consider a 3D sphere. Consider it an orange or tennis ball or a planet. And given what we know so far about OpenGL, which is a decent amount, can we create a model for that spherical shape using what we know about OpenGL? I give a couple possible equations to use, but normally when you're dealing with something circular, radial, spherical, doing polar coordinates is usually the way to go. You can think of perhaps you're drawing a quad on this, and each quad would have two angles associated with it. So let me probably make this a different color here. If we know that we're going to compose this object, and ultimately it's triangles all the way down, but let's think about it as a rectangle along the way, and we're going to specify the vertices for our particular rectangle, then there's going to be two angles associated with that. There's going to be the angle around the one axis and an angle around the other axis. So while you can technically use an explicit form of a sphere's equation to kind of come up with x, y, and z values, the more conventional way to do it is use angles phi and theta or u and v here, and using those equations, just basically generate those coordinates for x, y, and z, really for which any pi or 2 pi circle is going to suffice for u and v. V would be the one that goes all the way around the circle, and then as you're rotating that, you're also rotating your u from negative pi over 2 to pi over 2, and generating, like anything else, generating quads, generating triangles, and having them kind of compose together to make a circle or a sphere at the end of the day. Let's take a few minutes thinking about really not the OpenGL calls. We know it's going to be a buffer with a bunch of vertices at the end of the day. But what would those vertices look like? What would the code you would write look like to be able to start to generate the individual components that could be combined together to make a sphere? This is our first attempt at in-class 3D modeling, and like all of your 3D modeling, it's going to look bad. And that's okay, but there's a point to this. So let's take a few minutes, team up with somebody if you're kind of physically separated from the rest of the class here, and discuss. One of you has done this a little bit already for some of the MP demo assignments, but for the rest also, let's just discuss what kind of x, y, z values make sense for this 3D sphere here. Let's take no more than 5 minutes, because no matter what you come up with, it's not going to look very good, and that's kind of by design. So middle rows here, why don't you guys talk with each other briefly? You guys are focused on other things.
Yeah. Weird things about like all the squares and triangles. We're gonna do right. So they're half like
Those are meant to be quads. I'm drawing with my trackpad here. Those are meant to be rectangles.
as you go from like top to bottom, it's just like shapes of because all the quads are evenly surrounded by 4 pieces, so. I don't know how you do this. I know you can control the vertices in your vertex buffer.
Sounds
You only have to specify each vertex once. Whereas like if you have the strips, you end up duplicating where strips connect. But I don't know how you do it. Like in the code,
Or like just 5. Yeah. It might be like 5 triangles.
if I have a rectangle and then I move to the right, down, and then over, then I'm duplicating the vertices, like at that corner, if that makes sense.
That's a good point. I wouldn't worry about it too much. You may wind up sending more vertices than you strictly need for doing this. That's a valid point, but not what I'm terribly concerned with right now.
You could have start at the top, vertical most.
So for more like
define like
complex, pretty looking shapes in
down
like real life, whatever someone would like to design and render it, and then OpenGL can just take a object file.
Yeah, we'll talk about that. And I heard you talk about how, it's gonna look very triangle-y, but that's really just a function, well, it's a function of how well I can draw these. That's just really a function of how small our triangles are gonna be. So we'll talk about that. We'll talk about both those questions. Hearing some good discussion here, but I know that you're not gonna get to a fully fledged, solution for this. One reason the polar coordinate solution is the easier way to do this is because just kind of naturally leads to a straightforward programming implementation of it. I have a variable phi, I have a variable theta. This was my attempt to draw kind of a strip of these quads, and what you're supposed to kind of see is, well, each individual quad or each individual triangle is flat, but as you set those vertices, you're kind of going around, I don't know if you could see it, you're kind of going around the ball, and you're doing that negative pi to pi kind of rotation around the ball, and then you just have to also then do it as you're doing those for this axis as well. So you have this u and this v, or this phi and this theta. You have a range for both of them. What we don't have is how discrete we want those to be. Do we want big triangles or little triangles? But no matter what you choose for that, like the number of steps you're going to have to get around the sphere in either dimension, what you have is basically a double nested for loop, right, for generating your vertices there. For I is negative pi over 2 to pi over 2 via some step, and for j equals negative pi to pi via some step, do a GL vertex or generate the next entry in a vertex buffer object with these 4 points, where if this, and again, this is really, really mediocre drawing here. If this is our point at ij, we also do theta plus some delta. We then do phi plus some delta, as well as just this, in this case, phi and some delta and theta and some delta. So we can just generate our 4 points that way, and we just continue as we make our way around the circle. There's other approaches. A very common approach to drawing spheres is to do that for all like the main part of the sphere, and then instead do a triangle fan for the tops and bottoms for the poles, because there you can get pretty good precision with a fan type object versus these strip type objects, but you can do it with strips as well. I'll show you a piece of code that attempts to do so, that when I say it doesn't look very good, I'm referring to my own code here. This is using old school fixed function OpenGL, but it doesn't matter for our purposes. It does the exact same thing as just setting entries in a vertex buffer object. It's just easier to kind of look at the code and see exactly what is happening each step along the way. And it's exactly as I was starting to mention here. So old school OpenGL, we're going to make everything blue. So I said draw an orange or a tennis ball or okay, it's drawing a blue planet is what we're drawing for this one here. So we're drawing a planet and everything's going to be entirely blue here. And there has to be some parameters which is dictating the density of that mesh that you're constructing. That's our num point parameters. So for these quads in both the I and j dimension, we're going to be having a specified number of points associated with it. And otherwise, effectively, you're just plugging in those values. So first you would start with what would be thought of as in this visualization, maybe the lower left vertex in a quad strip there. Then I say u v plus 1. So we take our phi term here and do plus or minus pi over num points. So that would be, next we would be doing this point. Then u plus 1v would then be specifying this point. And then I take my word for it, the last one is u plus 1, v plus 1. We've specified 4 points for a quad here. Now, if it's a quad strip, in theory, then we only have to specify 2 more points. We're not wasting our vertices. But even if we do wind up wasting vertices, it's just a little bit slower, but you're specifying all the vertices for a quad as it goes in that direction. And then you're incrementing your u and v values as you go through your I and your j loop here based on that num points parameter. Little bit of trust that this is doing what I'm claiming it's doing, but let's see what it looks like in practice. I think it's just called sphere. Let's turn off. I did a mesh with the strip here. Let's see what I have here. Give me a second. Let's turn, hold on. Lots of options here. Okay, there we go. That's what I wanted to show in the first place. So that is our sphere. What's wrong with our sphere? I know I had a couple different options I was going to show here. It is a circle. But it's funny though. This is an orthographic view. So that's of course part of the region. But even if we had a perspective view here, you're still kind of looking at a flat view of the geometry here. It is a sphere. But a sphere in which everything is the same exact color. Everything is blue and the same amount of blue. Does not in fact look very spherical. Now one of the options, and my keyboard is making this a little bit harder than I had wanted, allows you to just by changing the parameter of how you're rendering it, allows you to specify that you want to render a mesh versus filled quads. We generally only do that for kind of visualization purposes. Normally we want our things to be rasterized and filled and not just the outlines of it. So when you do that, it looks spherical, but that's kind of a trick that we're intentionally showing the outline mesh. And you can confirm, yes, there's actually 3 dimensions here. It does look spherical, but that's not generally what we want. We want a globe. We don't want a ball-looking thing. It is also not necessarily a function of the geometry, like the num points parameter in the code or how many triangles or quads we're using to render it. We can lower it, and that's what I'm going to try to do here. That made it smaller. Somewhere I can specify, that I want to lower the number of points here. Let's make it even a little bigger so we can see it well on the screen. We can lower the number of points we're using here. Well, there's a limiting function here. Yeah, that is technically following our sphere equation, and it doesn't look very spherical, and eventually it's just a line. So there's a limit, in terms of the number of points. But even as we're, really cranking it up, and I don't want to necessarily crush things here. Let's make sure I did this correctly. There we go. Even as we're cranking up the number of points here, you really shouldn't see any change at all. It still looks spherical. Maybe the main difference is around the edges. It starts to look a little crispy, right? A little less rounded around the edges, and I cranked it up quite a bit, so I got to go back down quite a bit here. Yeah, I knew that was going to happen. Let's rerun it. GPU memory usage is at 99%. Okay, good. All right, let's go back to where we were. Okay. I was pressing the wrong thing here. All right, I just did it again. Doesn't take much, right? One more time, folks. Okay. I have the function key, which is I'm using to make it larger versus more geometry, and it's kind of hard to see. Nor is it the fact that it's a static scene, just to make sure we're clear what's happening here. Certainly, when I rotate and I'm seeing I'll make it a little even smaller, I'm seeing my mesh here. Yeah, it definitely looks really spherical, and it's a rotating Earth and whatnot. When I turn off the mesh, which again is normally how we would want to render it, Maybe you can see it's rotating because you can see a little bit of wobble around the edges, but it still just looks like a circle. It definitely does not look like a sphere here. What makes it ultimately look like a sphere in real life? What makes our orange look, or our tennis ball look spherical, and not just the fact that it's in that rounded kind of shape? Actually has to do with the lighting associated with it. So here is it with the code with the lighting, a lighting model turned on. The same kind of lighting model we'll be able to implement here. And we're not running a lot of polys here, so if we want it to look really smooth, we can up that a little bit more. And now it looks pretty spherical. We can turn off the rotation now. What we will learn starting today, and then I guess going into next week with Thursday being our demo day, is kind of the mathematical techniques and the corresponding shader calls that allow us to go from that to this. And there's going to be two steps to it, because there's two different kind of flavors of shading, and one of the teams is going to explore that potentially for your project. One is in which we're kind of treating every vertex as what we're interested in shading. So per vertex shading is what's happening in this render right here, where it definitely looks three-dimensional. I would argue it looks three-dimensional. But what can you really see here with our lit per vertex lighting? You can really see the polygons. And you can get rid of that issue by just throwing more polygons at it. I got to be a little careful, but that's a decent number of it's exponential, right? As I increase, every time I press the up key, it's quadratic. The number of polygons I'm adding here. I don't see them anymore, but I've solved quote unquote that problem by just throwing a ton of vertices at the problem. That does work. If we go back to our somewhat more modest, maybe reasonable number of vertices here, there's both approaches we can wind up doing. We can do per vertex shading, where the light equations that we're calculating is done in the vertex shader on a vertex by vertex basis, and then the rasterizer does the rest. Maybe you can even kind of see that, right? There's kind of traditional gradient-based rasterization going on here, but then you can also choose to do the lighting model on a per fragment basis. And here, that did not look much better. Maybe I have to go to less geometry here. It looks different in this case. As I increase the geometry, it looks very smooth here. Let's get it spinning instead. For this demo, it doesn't look tremendously better. I'd have to check if I didn't mess something up. But it should be now you're calculating the lighting per fragment and not per vertex. And it should be a smoother looking lighting model as applied to it compared to doing it otherwise. There we go. So the math is fine. You very rarely have to render your own sphere from scratch. But understanding why I think this looks bad is what's important here before we get started. Why we need lighting in the first place. That's not to say as you are specifying your own geometry manually, you're specifying your color values in that buffer, your vertices, there is nothing stopping you from specifying all of these color values that happen to have gotten calculated here, right? They're just RGB values. You could manually calculate offline what those values should be for a certain light source and do that. But what we have are mechanisms to do so in the shader without having to calculate for every single vertex offline what that interaction would be. And that's what we're going to talk about and learn today, and at least start today. Okay, so those are our objectives. We're going to learn to shade objects so that it looks more three-dimensional, introduce the types of light material interactions. The only part I think that gets difficult about that is that there's just a lot of parameters, and you have to have a decent grip on what is a reasonable set of parameters that you're interested in exploring. And we're going to talk about the modified Phong or the Phong-Blinn model and how that gets applied both mathematically, what is happening there, and then just in the practice of doing shading in our vertex and fragment shaders, what that winds up doing in modern hardware. So why we need shading? I think we got it. Our blue sphere looks like a blue circle here. We did all the work to figure out three-dimensional vertices and our positional attributes, and we didn't get something that wound up looking three-dimensional at the end of the day. Why does a real sphere look three-dimensional? At least in part, the answer is that the way light interacts with the material of our orange or our tennis ball or our globe, it does cause each point, whether we're thinking vertices or fragments, to have a different color or shade. And so when we talk about shading, that's what we're talking about. How do we determine what the final color should be here? In order to do that, we have to kind of break our current approach to modeling things, which is what is my positions and what are my colors, to instead specifying other attributes, both of our geometry as well as the rest of the scene. So we can still think of our vertices as having a color, but more commonly now we think of them as having certain material properties. We think now of our scene as not just having a set of geometry as well as our viewer being positioned relative to each other. We also need to think of, for our scene, what light sources are there in the scene and how are they going to impact the final shade of our objects here. In practice, how does light work? This goes kind of back to our why is the sky blue question from much earlier in the semester. We have some light, right? If there was absolutely no light in this classroom, everything was turned off, we wouldn't see anything at all, right? If it was pitch black in here. So we have some light source. We have some light in reality as well as in our scene we're trying to model. And the light is going to have something of a physical interaction with the objects in a scene or even in reality. Light is going to strike object A in the scene. Some amount of that energy, some amount of that light is going to get scattered. It's going to get reflected off at various angles. Some of it is going to wind up getting absorbed. Why do certain things absorb some light parts of the spectrum and scatter others? It has to do with material properties. That's the best I can explain it. Why are certain things purple and other things aren't? Likewise, then, once that initial scattering happens, some of that scattered light is going to strike other objects in the scene as well, and so forth. Some of those light rays are going to get scattered, and some of those are going to get absorbed. Ultimately, there's an integral equation associated with it that's referred to in general as the rendering equation. You have this infinite scattering and absorption of light in a scene. In a sense, it's an equilibrium equation where we're trying to figure out the total energy equilibrium of a particular scene that we're trying to render here. Given an energy source, giving a light coming into a scene, oftentimes we think of the light as being a reasonable distance away. Where does all that energy go? And we're trying to calculate basically the optics and the physics of how does that light transport happen? Where do these rays of light wind up going? Where do they get scattered? Where do they get absorbed? In general, the rendering equation can be specified but can't necessarily be solved analytically. And our solutions for how to do lighting in a 3D scene are basically different numerical approximations for solving the rendering equation. One of which that you probably would have heard of is the concept of ray tracing. It's a special case where there is a numerical solution where we have these reflecting surfaces. But the rendering equation is in general something that we are aware of from a physics-based rendering perspective exists. We are looking effectively for approximations to the solution for that rendering equation. So while this view of what's happening in the scene is a correct one, generally, unless you're doing some sort of ray tracing type of implementation, if you're doing conventional 3D rendering, you're not necessarily trying to model the physics of light transport. You're instead trying to come up with an approach that gives a reasonable approximation to what is happening in reality, in which we do have light sources. Those light sources are scattering, reflecting off various surfaces in your scene. Consequently, they're causing shadows here. Likewise, those scattered reflections are going to bounce multiple times until eventually all of that light gets absorbed and you reach kind of the radiance equilibrium in your particular scene. So you'll also hear this term of local versus global rendering. The other term you'll hear is global illumination or indirect illumination. When we talk about global, that means that the group of algorithms that are still used quite a bit in 3D computer graphics, but less so in real-time computer graphics. And those are the algorithms that attempt to impart realistic lighting to our 3D scenes. Those are the algorithms that have to take into account the rays of light that come from a source and get reflected along the way. Now, this field is rapidly changing. There was a time where I would say when you have your offline rendering, that tends to be more likely to use global illumination. When you have your quote-unquote real-time rendering, that tends to use this second way of doing things, this kind of approximation approach. That is changing, and that's changing as hardware is evolving to support more of the mathematical operations required to do global illumination in real time. But it's changing, but it's still not necessarily there. That by and large, what you tend to have for interactive 3D rendered scenes is by and large, the majority of the rendering is still using so-called rasterization-based approaches with some global illumination effects thrown in. So the vast majority of the rendering is still using the approach we're going to be talking about today. And then there is still some to make nicer looking effects, to get proper reflections, to have more realistic looking shadows. You wind up getting some of this thrown in as well. So modern today, 2023, it's a mixture of both. We have to kind of learn the traditional approach first, and then as time allows this semester, we can start to talk about real-time rendering using a global illumination-based techniques here. Kind of covered this just to make sure we're all on the same page. We have the light material interaction, and understanding that this at least happens is necessary for us to do even this local rendering approach, lighting approach that we're interested in here. We have light that strikes an object, some of that light gets absorbed and some gets scattered. That's due to, I think all we can say is the material properties of the object. It's back to why is the sky blue? It's because of the material properties of the optical properties of the molecules of air in the sky cause the blue light to get reflected, scattered, and the rest of the spectrum of light to get absorbed. But as we were answering that question, even though it's kind of a tongue-in-cheek question earlier in the semester, part of the answer is the sky is not always blue, right? That's a good way to think about this issue. The sky is blue under certain conditions, under certain lighting conditions, under certain atmospheric conditions. Likewise, why is that bag green or why is your shirt red? It's not always or cardinal, excuse me. I don't want to offend our Iowa State Cyclone fans here. It's been through the cycle too many times. It's really just red now. The answer, first off, is it's not always red. It's not always cardinal. In particular lighting conditions, given certain material properties of it, it's going to appear to our eye to be a certain color. If we get it completely wet, maybe it'll be a slightly damp or darker shade of red at the end of the day. If we turn off all the lights in here, right, it's going to look extremely dark red or even black. We won't necessarily even be able to see it at all. If we change the color of the lighting sources in here, and I'm not even talking about black lights and blue lights and things of that nature, although that would certainly change the color of it as well, just changing the color tone of the lights in here. If we go from fluorescent bulbs to LED bulbs that have just a different light spectrum associated with them, the color of all these things that we perceive are going to change. So ultimately, this is still happening, right? It's not as straightforward as this object is green. Sometimes it's green, other times it's different shades of green, other times it can appear to us to be different colors entirely, and that is a function of both those things that are happening here. The properties of the light source itself, again, if you really want to think of it, I replace all the bulbs with blue lights or black light bulbs, that will change the color of everything we're interested in, and it's the material properties of the object itself that dictate what color it appears to be for us as we're personally viewing it with our own eyes. Similarly, as we try to model this in a 3D scene, how we want to model the particular objects in our scene. General light sources, like the ones we have in a room like this, can be difficult to work with. Not necessarily impossible, but just complicated, because what you have, even for a single light bulb, is you really don't have in practice a single light source, right? You have this, in this case, incandescent bulb here, but even if it were an LED bulb, you have an individual source of the light, but then you have this actual bulb that's already doing some of the scattering. What may appear to be a single light source of a single bulb could in fact be multiple different light sources in a particular scene. In practice, what we do is we define simple light sources of a couple different types. We define what's referred to as a point source, where that's just a model that we have a position of where the light is and we have the color associated with the light. White light is fine. There's nothing wrong with white light, but we may want to have different types of light in our scene. And for some aspects of the calculation, we assume that there's potentially a distance source, where that light is sufficiently far enough away that we assume the rays that are coming off it are all parallel to the light source. And we're not worried about the actual interactions beyond from that location of the light source to our geometry. We only have to really think of it as being a single vector in our scene. There's also ways of specifying or considering things like spotlight sources. There's also this concept of ambient light. Ambient light is also just a sort of numerical simplification of what's happening in practice, where if you want to make sure there's some amount of light everywhere in your scene, you add this kind of background lighting, this ambient lighting. That allows you to model the contribution of what may be many complicated sources. We may be okay in modeling this classroom of just having perhaps a single light for the projector and then just general ambient lighting here. It wouldn't be that accurate, right? The back of the classroom, and depending on how many lights we turn on in one day, are darker than the front of the classroom. But as we attempt to model that, we do want to make sure there's some lighting at all in the back of the classroom. So while in reality, why is it still light in the back of the classroom? Because there's this infinite scattering of rays of light going from all these different light sources. In theory, that's the reason why it's the case. In practice, we may just want to say, well, let's add a little bit of background light so that we make sure that nobody's completely in the dark as we're modeling this classroom scene. So you heard the term ambient lighting. Let's turn on some background lighting. Let's turn up the dimmer switch a little bit. That's what it kind of is. It's sort of a global term we are adding to the rest of the lighting we're interested in to make sure that no matter what, we have a little bit of lighting for every one of our objects in a scene, even if it is technically not being directly lit by any particular source. Let's talk surfaces as well. The smoother a surface is going to be, the more the reflected light is going to be concentrated in the direction that a perfect mirror would have reflected the light. Versus if you have a very rough surface, it tends to scatter light in all directions. Think, unfinished versus finished wood, I guess. I was going to use this as an example of finished wood, except it's really kind of worn out. But, the reason you see these so-called specular highlights is because for some aspect of this material property, it's kind of directly bouncing the light back off. It's closer to a mirror than it is to anything else. But if you take a regular 2x4 that doesn't have any finish on it whatsoever, it's not going to have that. It's going to have just kind of a general equal scattering of the light in all directions. It is going to look like a brown board, kind of a flat shaded brown board there. So as we start with the Phong model, there's a small amount of math to keep track of. Nothing I think we can't handle, nor is it necessarily something we have to really derive from base principles. I think being aware of it is probably going to be sufficient for a learning outcome from our perspective. The whole point of it was to develop a lighting model that can be done quickly. It was, a hack in a good sense of the word, that there's this mathematical model of global illumination, way too computationally intensive back when this was invented, and still to some extent today to be able to do in real time. Can we get a reasonable real-time hack to be able to use software, later GPU hardware, to calculate this lighting model in a much faster amount of time? So we start with, there's going to be 3 lighting components that we're calculating for all of our geometry in the scene. There's the diffuse, scattering component of our light. There's going to be the specular or the reflective component of our light source and our material, and then there's the ambient, the background light. So already there's 3 things to keep track of. In order to do these calculations that we'll talk about here, there's going to be 4 vectors that we're going to have to keep track of for our particular scene. There's the actual light source. So again, we're going to be specifying a position of our light source that's going to correspond to a light vector L. For sake of simplicity, we're going to assume it's effectively infinitely far away and there's a single vector coming in, and we need to have that vector in mind. We also need to know the lighting normal. That is how we're telling OpenGL, how we're telling our shader that the object is going to reflect light around a vertex. You can think of it as there's a small mirror at each vertex or at each plane we're interested in here, and the lighting normal is dictating where that mirror is oriented for our particular vertex. We can either calculate that or we can be provided those values. We still need to know where the camera is, we still need to know where the viewer is, and then as part of this calculation, we do need to separately know for our light, where our particular vertex is, what that perfect reflector would be of that point P that we have here. So there's a decent amount to keep track of. Let's talk about what that means in practice. I think I mentioned. So you have your surface normals that define how the surface reflects light. Again, you have your geometry of our x, y, z for a particular triangle or a particular vertex. You then, to do a lighting model, have to separately specify a completely different vector. This is our normal. This is the mathematical definition of a normal. It is the orientation of that plane here, or we do it on a vertex by vertex basis. The application is responsible for providing those normals. I didn't really emphasize this as we were looking at our sphere.c, because again, this is kind of old school OpenGL, but every time we specified our GL vertex call to specify our XYZ location for the next vertex in our quad strip, we were also specifying our normal as well, our normal to that vertex. There's a little bit of a hack because this is a sphere, and you can have a sphere be modeled as the normal being just equivalent to the XYZ value, because it's assuming it's centered at the origin and everything is pointing outwards. For your XYZ, that can also be your normal as well. So that made it a little bit simpler. If this wasn't a sphere, that wouldn't be a sufficient way of doing it. In practice, we can calculate the normal given 3 points in a triangle by using the cross product. For some of these calculations that we'll briefly touch upon today, we need the normal to be normalized, so we need it to have unit length for the rest of these calculations to make sense. So there's a decent amount of math that your application would then have to do. Given a certain amount of geometry, when you have your XYZ values for your 3 points that make a triangle, before you go and actually start to render those triangles, calculate the normal value as well, either offline or doing it live, and pass those normals along with the rest of your geometry for every single polygon. That can be a little bit painful, so oftentimes when we're dealing with object geometry, we're dealing with rendered models or determined models for a particular scene. Here's just Windows 3D Object Viewer, and the only model that I've been using so far. There's other ones in that directory that you can choose. This is our seal model, and it was an output from Blender, taking a 3D CAD for a 3D printed version of a seal. And here's our output that you can see. Yes, it's a nice looking seal. The actual contents of this file is a wavefront OBJ file. Has anyone played with those before? They're flat text files that are really just a way for your application to specify this stuff in advance. So that your application, you'd probably want to write a utility that loads these files, but your application doesn't really need to worry about this aspect of it at all. It doesn't have to do that calculation for you. A tool like Blender will generate this for you. This is the same exact file. Here it's opened up in 3D viewer in Windows. Here is the actual just text contents of that file as outputted from Blender. Let's see if we can figure out what's happening here. V and then 3 points. What do we think that is? Vertex, right? Now, this format doesn't specify triangles. It's not trying to render it directly, at least in this initial specification, right? It's saying, here are the vertices of interest in my seal. Some of them might wind up getting repeated. You can make triangles all sorts of different ways, given a mesh, given a set of points in the XYZ space. What kind of coordinates are these referred to as in our viewing pipeline? These are our model coordinates, right? These are coordinates, you got it, it was one of the two. These are coordinates relative to the object itself. These are coordinates that, this is what Blender provided, that are only meaningful to the object in kind of isolation. Again, eventually, we put the seal into a scene. Those have to get translated into world coordinates. We then choose a camera and an appropriate lens for the camera. That then translates those world coordinates to our camera coordinates. We then do our clipping and things like that. But these are our model coordinates. And this is a pretty hefty model. And this gives you a general, this isn't actually the amount of triangles, but we can get to that number. But it's going to be roughly equivalent to the number of triangles unless something really weird is going on. So we're looking at some 13K triangles in this seal. So if your seal doesn't work, it's because it's just doing a lot of stuff, and there's a lot of places for your rasterizer to go wrong. That is just the specification of every XYZ valid for this model. Now, as part of that Blender output in this OBJ file, we're also specifying the normals. These should be unit vectors, and there's no direct relation between the V's and the VNs, but that's what we're specifying here. Here are all the normals associated with this particular object that we're rendering here. Later, if we were doing texture mapping, there would then be texture coordinates as well that would be specified for all the different texture coordinates we need to have here. And then finally, usually at the end of the file, and you can include other files, I lost it here. You can include multiple shapes in this file, you can include other files within these files. You finally have your declaration of the faces of our object here. The double slash is just that we have skipped information. So it goes vertex, texture coordinate, vertex position, excuse me, texture coordinate, vertex normal. This is an untextured seal. So it's just blank for that texture coordinate, but we could have rendered a textured seal, excuse me. So that's what that's specifying. I'm not going to scroll all the way back up because that's getting kind of painful here. But the first, third, and fourth vertex in that list are what make our first triangle in our seal. The fourth, fifth, and sixth triangle in that list, fourth, fifth, and sixth vertex on our list make the second triangle, and so forth, with the normals given by the first, second, and third normal in that particular list. They'll try to minimize the amount of redundancy, needed in this file format. So it's not always as straightforward as 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9. But effectively, that's what that is. So now, given this list, we can actually answer exactly how many triangles are in this model. We would have to do like a quick analysis of that. We'd have to do it was F, right? Lowercase f, or was it capital F?
Lower.
We got 27,200 faces in that seal model that we have there. So a decent amount, and more than the number of vertices that were specified there, because you can combine them in various different ways. But it's that normal that allows this, and in this Microsoft application, it's basically doing a render of it with some arbitrary choices you can choose to change. It says light rotation here, where the light source is in our particular scene, and you can start to see the sun setting on our seal here. I guess over time. You can also I haven't played around with this application much. You can specify for that particular light what the properties of that light is going to be. HSV kind of makes sense, but I feel a little bit better thinking about light sources being RGB. Why is our seal gray? Various tones of gray. It's the same question as why is our shirt red or the backpack green? It's because of the interactions of the material properties of the seal, which aren't specified at all in this application, and the properties of our light source. So the seal is red because we've specified our seal is white because we specified our light as being white. If we no longer specify our light, there may be multiple light sources in the scene. So to make this look good, I may have to turn all these to red. I haven't played around with this. It's getting there. Still purple because of that last light here. So our seal is not white anymore, right? It's there may be some ambient lighting here. Is that what it's listing under environment? So they're calling ambient. OpenGL would call this, ambient light source. And if we turn that to red as well, now we have a red seal. And this is just an application. This isn't a rendering application. This is a modeling application to see the 3D models that you have here. So why is it that color? No longer because we're specifying color attributes and we're saying we want this vertex to be red and this vertex to be a little bit less red. We're instead, the only thing we're specifying here are vertices, vertex normals now, and then separately kind of sort of hidden underneath the details of the implementation of this particular piece of software, material properties and those interactions. So let's talk about what that math requires in practice, and we can render our own seal that way. The takeaway from this is that, yes, while you can calculate your normals yourself, usually when you're modeling real objects, you don't have to. Either there's a mathematical model for the normal, like in our sphere, or as you're rendering and using Blender and other 3D software, they'll generate those normals for you. Yeah, go ahead.
Yeah, so I guess when you have the normals in like the model coordinates, you assume it's centered at the origin.
Right.
Then when you like move that somewhere else, do they go through the same kind of transformation matrix?
And it's something I've been I've been hinting at a little bit, and part of me is going to want to wait a little bit to like fully show this up, but if we go to our flat shader, and this is getting a little bit ahead of ourselves, but exactly that is what is needing to happen. So we have our model view and projection matrices. We can apply separately the model view matrix to our normal, but then when we do so, we have to make sure we renormalize it. We have to make sure it's still a unit vector, because once you've done that scaling and translation, it's not going to be a unit vector anymore. And then we don't typically apply the projection matrix to our normals, because that doesn't make sense. The camera doesn't change what our seal looks like and the properties of our seal, but the model view matrix does, right? We're stretching, we're rotating, we're scaling our seal to fit into the world. We do have to apply that same math to the normals as we do for the geometry as well.
Could you take the final vertices and calculate the normals, or is it preferred to do that?
You know, the issue though with, you know, if we're talking about programmable shaders here, the shader is looking at one vertex at a time. So you really can't, it doesn't know the triangle that it's a part of, so it really can't do that live calculation. You can do it always offline, but you can't do it live necessarily.
So you would take the normal of the entire vector and just put that in for each vertex.
Yep. And we show it here in our old school OpenGL, because there's an old school call to specify the normal per vertex. In modern OpenGL, it's just another buffer, and it's just another vertex attribute. And of our 4 attributes we have in our simple graphics processor, one of those, if you're going to do lighting, should be reserved for the normal information that you would have there. Sounds like you've kind of got it. Let's just kind of walk through some of the details, and we'll end with one final demo of what lighting looks like in practice. Again, I think as a learning outcome for now, being aware that this is what the code you're going to be using is doing is probably a sufficient learning outcome for this. So first we're going to talk, there's the 3 aspects: specular, diffuse, and ambient. Ambient's okay, it's just a constant term, but we'll get to it. Specular is the little highlights that kind of look like a perfect reflection. The other one is this diffuse. The other term you'll hear is Lambertian surface, Lambertian scattering. I can't pronounce it correctly. We'll talk about the diffuse reflecting that's happening here. We're given a light source coming in. It scatters equally in all directions. We still have a little bit of math to calculate, because the amount of light that gets reflected is going to be proportional to the vertical component of the incoming light. How direct on is the light source to our particular object? We can calculate that angle theta of the light source and the normal of our plane or of our vertex. It turns out that, you may already know this, that if we have unit vectors for both our light source and for our normal, we don't have to actually calculate cosine of theta. It's equivalent to the dot product. So logically, we're calculating the cosine of that angle to get the vertical component of the light coming back off. In practice, in doing so, calculating the dot product is sufficient to determine how much scattering should be happening there. So if we have a light source and we have a surface normal, it should have a full reflection, 100%. If it's at, let's say, an angle theta, there should be a partial scattering via this diffuse light scattering that we have here. And if it's perpendicular, there shouldn't be any. And that can be modeled using Lambert's cosine law. And that's why this is referred to as Lambertian scattering or just diffuse scattering. You could, if you chose to, calculate that angle yourself between L and N and calculate cosine of theta. If L is normalized and N is normalized, meaning they're unit vectors, the dot product is equivalent to the cosine of that angle between them. And it's kind of hinted at here. All of that would be calculated based on the coefficients of both the light source and the material as well. So again, why is the object green? Even ignoring any specular reflective highlights. Well, not why is it green, but how do we model it as being green is the better question right now. We model it as being green by specifying a certain property of our light. So you can think of it as IR, IB, and IG for this aspect of the light model. Like we did in this application, right? We turned for the 4 lights that were here, but for these first 3, I guess, we made it all entirely red. But then we would have to then separately specify for our object or for individual vertices in our object what the material properties would be for that part of the object. That would be how much of red, blue, and green are going to get reflected versus absorbed. Most surfaces are neither, perfectly reflective or ideal diffusers. Like our sphere example we had here, smooth surfaces tend to show these specular highlights during the light that's being reflected, concentrated close to the direction of a perfect reflection. So you have a finished piece of wood. Most of it looks like just kind of the flat color. When you have a light source, you can actually see that reflection in the wood because it is acting closer to a perfect mirror effectively for some aspects of that wood. That allows you to see where that particular light source is reflected directly in the material, in the object that we have here. This is then a different aspect of the Phong modeling equation. He proposed using a term that dropped off between the viewer and the ideal reflection as it increased. So if the viewer is directly looking at that angle of ideal reflection, it'd be the highest amount of highlight. As the viewer and the perfect reflector started to increase, that cosine would start to decrease, and he also then had some so-called shininess coefficient. So what you would calculate then is that perfect reflector of that light source compared to our vertex. You have to then know where the viewer is, because where this reflection happens is relative to where the camera would be in our particular scene, and then it would just be raised to some power alpha to determine how shiny that particular parameter should be for this. So given incoming intensity of light, and this would be calculated for R, G, and B separately, given some absorption coefficient for R, G, and B separately here, you would then have to determine for where the light source is located, for where our viewer is located, calculate effectively V dot R and raise it to that power alpha to get our specular highlights here. And you can just see a very quick example of what that looks like in practice for different values of alpha. Values of really high alpha tend to more concentrate the amount of specular lighting that's reflected around a relatively small amount. As our angle phi grows with very high alpha, that value goes to 0 very quickly. So you tend to have very small specular highlights. So this would be low alpha, this would be large alpha. It's not a matter of one being wrong and the other one being correct. It depends on what you're trying to model. Do I want to model a very metallic looking object or a very shiny looking object? Or do I want a somewhat shiny but still kind of flat looking object here, maybe more plasticky looking surface? You would have a smaller value of alpha associated with it. With alpha equal to 1, you get something that doesn't look so different than just our diffuse lighting here, but you do see still effectively a highlight across one face of that object. Finally, the third term of our Phong model is just the ambient light. So that's, in reality, we do have ambient lighting, and it's due to a complex set of interactions of all the different light sources we have in a particular scene. For our purposes in modeling ambient light, we just add one more term to our diffuse terms and to our specular terms of how we reflect for RG and B, the ambient lighting, and then the intensity of that ambient lighting in RG and B. We also have to be concerned with the distance of our particular light source. This is more so for old school fixed function OpenGL, where we would specify this A, B, and C term, but we're basically specifying how much our light is scaling away. If our light source is very close to the object, how much intensity there is versus if our light source is in practice very far away from our object. You can get pretty good looking scenes without having to worry about this particular term too much. But I do want to just mention that ultimately you have a lot of coefficients in your Phong model here that you have to kind of keep track of. For a lot of the rendering we would do, you have a shader for a particular object you want to render. I want to render this seal as part of a larger scene. You are going to need to have, and generally would have, a shader for that seal. And as part of that shader, you would be specifying generally as uniforms all of the properties of both the light source as well as for the material properties of that. So we mentioned 9 coefficients per light source here. There's also an additional 9 coefficients for the material properties as well. There's a lot to keep track of. Again, if you assume all light is white, then you can simplify a lot of that, of course. And if you assume, some sane defaults for what you want for your material properties, then that's not too much to keep track of. We also then have to keep track of that shininess coefficient as well, that alpha term that we have here, and I mentioned that. So for each light source, there's 9 I values, or 3 vectors of I values for ambient, diffuse, specular. That's for each light source. Then for each object, We have those 9 material properties, those 9 absorption coefficients, as well as that shininess coefficient alpha here. That's the Phong model. Ultimately, you take all those components, and for each light source, the answer to why is this object blue, or why is this vertex going to be shaded this particular color, is based on the combination of all the light sources and their interactions with that object. So for every light source, you determine how it's going to be the diffuse reaction. You determine if there's going to be any specular highlights and how much that's going to add to the color, and you determine the correspondence or the addition of the ambient background lighting to that particular object. So there's a decent amount of additional math that has to get calculated versus just saying, I'm specifying this vertex with an attribute of color of blue. But if you want to have your sphere to not look like a circle, that's what you need to have, right? You need to have some lighting model that you're calculating here. I'll show a demo of this in just a second. That can be the last thing we touch upon today. You'll hear the term, so Phong model is still very commonly used. You'll hear this is Phong lighting we're applying to this scene. The other term you'll hear is Phong Blinn or modified Phong, and it turns out that there are kind of textbook implementations that implement this. The term that's actually the most problematic is this V.R for reasons that are a little bit subtle, but based on what we know, I think we can walk through this. L is a property of the scene. We specify it once per frame. N is an attribute of our vertices. We're either given it or recalculated, but it's a fixed per vertex. It doesn't change. V is a property of the scene, but V.R is something that may change quite frequently depending on where the viewer is located. So the Blinn modified Blinn Phong model or just modified Phong model is doing is not to use that V.R calculation, which already itself is a hack. So there's no harm here. We want something that winds up looking reasonably good with a relatively tractable amount of effort here, was to use the so-called normalized halfway vector between L and V here, and to use that angle instead of this angle here. The thought being that they're not the same, but they're going to be the same order of magnitude, so we can get a reasonably close result. Yeah, sure.
Can you clarify what each variable represents?
Sure. So this diagram's got a little messy, but for this diagram here, so P is our vertex. It maybe shouldn't be called point, but that's our location, right? It has a normal. That is like if there was a mirror located here, which way is that mirror oriented? That is a direction, right? We have a light source that is also at a certain direction. That also gets normalized even if the light source is quite far away. To make the math for doing the cosines work, we have a normalized normal, we have a normalized light direction. That's for each light, so that's going to change per light, but that's how far away it is. Again, if this is our normal, I don't know, this won't show up on the video, and our light is here, there's no interaction, it's not lighting up the object. If our light is coming down here, it should give us maximum intensity, and everything else is just some degree that we're trying to estimate and calculate reasonably well. V is our vector to where the viewer is in our scene. That's our camera. And R, which we only needed for this component here, and we're actually going to get rid of in a second, is something we would have to calculate. Given our direction of the light, it's just the same angle, but what is the perfect reflection of that on our surface? So this angle here would be the same as this angle down here. We still have to do that calculation. And I think it's sufficient to say that that extra calculation of R dot V, even if we don't have to do the cosine, we can still use a dot product for it, is something that changes more frequently than this approximate hack of looking at L and V and calculating this angle instead. That is the only difference between the Blinn Phong model and the regular conventional Phong model, that this angle is not the same, and is never guaranteed to be the same as this angle, but it's going to be the same order of magnitude in practice. So the modified Finn model is just replacing V.R with N.H. Since they're not an identical angle, you would also change this kind of arbitrary synthetic coefficient of shininess with this different artificial, created coefficient of shininess, and that's the modified Blinn Phong model, and was for many years basically the standard in OpenGL. If you're doing lighting in OpenGL, this is the lighting model you're applying. Now with programmable vertex and fragment shaders, you can still implement this, and we'll see what that looks like in practice when implemented in our shader. But now you can do whatever you want, right? Just limited by what performance you want, how many resources it's going to require. So here's an example that kind of shows them all in one slide. This is all the same Utah teapot, and the only difference is the parameters in the modified falling model, right? And they look significantly different, and the reason they look different is just we're just changing the parameters. Some are shinier than others, some are duller than others, and they're different colors, not because we specified a color buffer in any way, shape, or form, but because we changed either the lighting properties or the material properties. You can't really tell necessarily. One potential giveaway, although the specular highlights are white, that usually means the material properties and the light properties were white at some point, right? Because that's how you get what the white lighting result when all of our RGB values are high. But otherwise, we can't necessarily say is the material properties or the light properties for the diffuse components that we have here. I have another one of those fun training applications, and that'll be our fun final demo for today. There used to be in OpenGL, as everything was a state machine, everything was a function that would change some parameter of the state, including all the different parameters of the lighting model as well. You'd have a function to turn on shading. You'd have a function, as we saw, to specify the normals, then separate functions to specify each of the material properties and functions to specify the individual lights. We don't need to do it that way anymore. We still have to specify all that stuff, but that can all be now a combination of vertex attributes we specify via our buffers, and uniforms we specify as kind of per shader constants as we're doing our programmable shading. Because I like this demo, we can run it. And if not, we don't have to. It's a little bit larger here. And it kind of seems sad that it's our torus model, but if we really want to, we can go back to this guy and model him instead. I feel like, though, that to be honest, the torus is better for kind of seeing what's happening here. And then you can change it to whatever you want if you want to run it yourself. So still, there's that part of the application we were kind of playing with before. Is this a orthographic view or a perspective view? The lower left tells us the answer. You had a 50-50 chance, so I'll give it to you. No, it's got that truncated pyramid kind of viewing frustum we have here. So it's a perspective view. You don't need a perspective view to see the lighting here, but it kind of helps to make things look more realistic. For a torus, it doesn't really matter all that much. That's just, again, just to show how we're looking at things and how things get translated as we're moving our camera around. What you're seeing here is that final white. Does that show up here? Yeah, this white component here, that's our light vector here. So somewhere in your application, whether it's via a uniform or some other mechanism, some constant in your shader, you are specifying a light position. That's that first vector, that's XYZ locations here. You are also specifying your material properties, which is for ambient, diffuse, and specular, what color is that light? In this case, there's no ambient lighting decision for this. We can change it. If we want to have really red ambient lighting, the end result is for the stuff that's not otherwise shaded, we're going to be adding more red to that particular light that we have here. Whereas our diffuse light and our specular light is entirely white here. Then in addition and kind of in concert with that, we're then specifying the material properties of our geometry here. That is ambient, diffuse, specular, emission. We'll talk about that in a second. It's not really important anymore. But for ambient, diffuse, and specular, we're just specifying what spectrum of the light is going to be reflected and which is going to be absorbed. For ambient, there's no ambient light, so it actually doesn't matter. For diffuse, it looks kind of grayish. And for specular highlights, it should look kind of blue-ish here, right? I mean, bluish is kind of a vague term. Grayish blue, right? Because we have equal amount of red and green and a little bit more blue. We can crank that up and have it look, even more blue as we do it. And that's what's changing here, right? That interaction is what's changing where our our colors are going to be. As we move our object, the only thing that is ultimately changing are those dot products, right? Where the light dot product with our normals is going to lead to more diffuse scattering, and where our half-wave vector, but our reflector is going to be changing with where our light source is, that's going to change where the highlights are. SE is that what we were calling beta. I don't know, that didn't look especially good. Maybe if I crank up that's already fine. If I make it, more, maybe it'll, okay, it looks kind of purplish. So now you can really see it at least. There's a little bit of contrast, so you can see it a little bit better. Those two aspects are going to change as we change. This application, we can change the light source. We can also change our object, which either changes our V vector and changes where our specular highlights are going to be, and why the backside is appearing to be dark, or kind of the shadowy sides appear to be dark, because of what that dot product between the normal and the light source winds up being here. You can also specify that your material itself has like light emitting properties. Let's make it green. So then it becomes like a light source. That's in a sense, and I don't recall, there's only one object in the scene here. I don't recall if that can be then treated as a light source to other objects in our scene. That's less common than otherwise.
What do alpha values mean for properties like this? Do they just not do anything, or
Let's find out.
whatever you want them to be?
What would it mean? So we could try to reason about it as our battery runs out here. For a specular highlight, what would it mean to have transparency? Again, we were able to show it a little bit better by cranking it up to pinkish here, right? And then cranking this value up so that it's more of a highlight than the whole thing. What would it mean to have a transparent? I think it would just change the value of those.
Like absorb more of the...
No, I don't think it's all that clever. Hard to say in this example model, because what does it mean for a light interaction to have like transparency associated with it? It's not clear to me. This is just a demo as well. We may not have alpha blending turned on at all. So my assumption would be it's a mathematical model. It would calculate, if we want to call this light ks dot alpha times light material ks dot alpha, and would generate not just the RGB value or the B value we're interested in, but also the dot alpha value we're interested in. You'd have to have alpha blending turned on for it to actually show up in the final render here. It should work. What does that mean in a real system? I don't know, but it would be a valid mathematical thing to specify for this. In the interest of time, let's leave things here for today. Thursday, demo day. I know you're excited. Come, ask questions. We can figure it out together. But I know you can do it. All right. See you on Thursday, okay?